This video will be about a scanning electron microscope made in Japan in 1973, and this device served as 5 different devices: atomic microscope, X-ray spectroscopy device, secondary and primary electron beam analysis, and about how crystals are being grown. One might think about diamonds. Well, might be true. We'll see. And that's the electron microscope, and there would be an explanation how it works. It's a gift from the friend.
So we're going like that. Electron gun, go down to anode, go down to lens, that's the lens, then is a focusing, and the focusing is done here, then it's lens number 2, and scan coils. The scan coils are being driven by, I don't know yet by what. But then you have electron beam again down here, and the specimen. There is something called transmitted electrons, absorbed electrons, X-ray pulses. Oh boy, this thing has so many things to play with.
Owned by some old guy who lived on a farm in Illinois and was an amateur scientist. And he was, I think, 79 or
79.
He died. And his wife didn't know what to do with it, so she wanted to sell it. So I made her an offer, and she had some students or friends pick it up and put it on the pallets and ship it to me.
Whoa.
And it arrived, and I never had a chance to set it up, unfortunately.
Beautiful. I'm gonna do it.
Yeah.
So thanks to this gentleman who donated to me.
I sold it to you.
No. It's you know what? It's like a. It's like a. Okay, he donated by selling to me for the price that everybody wouldn't even buy the coffee for it or whatever. Doesn't matter. So I'm so thankful.
Well, they haven't set it up and running yet.
Yeah, it will. It will. I'm gonna invite you.
Okay.
Thank you. Yeah. Okay, so this was in here. This part. It's in here.
That's the sample holder.
Yeah, the sample holder. And there is something in here which must be important. There was probably something that was analyzed.
Could be,
Yeah.
Looks like it.
Beauty of the past. Beauty of the past. Okay, I'm gonna put it back here the way that it was. We're gonna put that cup.
It's possible that the chamber opens up by undoing these.
No. The chamber must be accessible to put the specimen because.
Well, that may be how you put the specimen.
Yeah, yeah, that might be also possible, but I think there are two ways of doing it. One way is that, and the other way is open up the door.
Yeah, but the door might open up by pulling out these.
Yeah.
You know, you said this one doesn't have a seat.
Yeah.
No,
No, it does. It does. It does.
usually these things
Yeah,
come out like
comes
this.
out. Right. Right. Okay. And this is a pump. Diffusion pump. There's another one here. How am I gonna put that in? The old monitor. It would be beauty to play the science with it. And we have another box. Holy schmoly. Another box. Isn't that exciting? Okay, we're opening another box. It's the same color. Okay, talking about the other cups. Yo-boo-doo-boo-doo. And standard reference material. High purity platinum. Okay, I got some platinum. And I got some more of stuff. And I have no idea. Mount 2, Mount 3. Okay. Isn't that the... Whoa! Gun. There you go. The electron gun. That's how the gun looks like. Holy holy, it's the first time in my life they can see that in a close capture. Okay. And whatever is there. Holy holy! Ha ha ha! I have no idea. What is that? Some of the stuff. Kex, California, model 2003 preamplifier. Beauty. All of that stuff. Okay, here we are. The beauty of the past. And we have box, EDXRF, collimator, oh boy. Okay. Well, tell me what it is. Because I don't know. This is some kind of holder. Okay. Yeah, the time to how the electron microscope works. Now we have some beauties in here. Ooh. And what it says in here, scanning beam, racking beam. Okay. So this is the top of it. This is from the electron gun part of it. Okay. Well, now what treasure do we have here? Holy schmoly! Absolutely beautiful. Okay, I'm digging into this one, trying to find out more. It appears to be complete set of everything one could dream of. And this is wrapped up, so this belongs to this set. Detector supply, PMT collector, PMT power, positioning horizontal, vertical, scanning the operational mode, brightness level. I'm going to micro, ammeter, amperes, multimeters, range. Oh, this is how I adjust the range, because I adjust the current to the gun. 10 to minus 6. 10 to minus 6, okay, 10 to 10. This thing's supposed to go to 22 nanometers, 20 nanometers. Coarse magnification. 10 to 3 times 10 to second, 1 to 10 to 4. Okay. Condenser lens. Okay, the lens. Medium orientation. It's a lock for it. DC kilovolts, 50 kilovolts. Ha 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 ha. Filament, aperture. And then we have this. And then we have again level, differential. Level, okay.
And this part will be dedicated to growing crystals at very special lab. I will not probably explain how to grow diamonds, but
Okay, you are right now at a very much exciting place, and that's what you see in here is a reactor. I'm not gonna show your face because unless you want me to. No. Okay. So that's what you see in here is a reactor that is making crystals, and my friend is gonna explain how it works. Actually, I had a chance to buy the same machine like that, but I missed that. That's the beauty of it. Okay, would you mind to explain what are the parts of it?
Yeah, this is a vacuum pump.
Vacuum bag, right? Diffusion pipe, based on oil.
This is an oil diffusion.
And how much pressure? How much vacuum we can get out? 10 to minus.
10 to minus 7.
10 to minus 7. It's like the microscope over there.
Yeah, typically you don't need much better than 10 to minus 7.
Right.
And then you have a vacuum pump too.
Yeah, so you have a wrapping pump in here, and the wrapping pump goes to here, up there to that pump. So when the wrapping is done, how much the wrapping goes to?
About 2 milliliter.
2 milliliter, okay.
But you typically turn on the diffusion pump around 50 milliliter.
Right. And then you have some beautiful electronics in here, and you gotta have to have this big, huge pipe for it.
Well, the big, huge pipe is to make sure that you get all the gas out.
And then you have an ion gauge. Now, how the ion gauge will work with it?
In what sense?
I know how to. For the people.
An ion gauge just has a filament inside it that ionizes any residual gas, and then collects the ions,
right,
to give you a measure.
And then it sends
actually a voltage signal to a detector.
Right.
That's proportional to the pressure.
Right. Okay, and then we have some nice valve over there, up there.
Yeah.
That's how is that valve operated? Hydraulically? I mean,
Pneumatic.
pneumatic. And what kind of pressure do you need for the valve?
Oh, 30 psi.
30 psi. Okay, that's normal.
Yeah.
And then we have some kind of yeah.
There's also another interesting vacuum gauge there, the capacitive manometer.
Could you say a few words about it?
The capacitive manometer is just like a diaphragm that deflects under pressure. And then changes the capacitance between two plates.
Okay. Now we have two openings in here. They are nicely closed. Usually people have a nice round piece of glass there.
No, this is very
too hot temperature. So what temperature is there?
This will go to about 3,000 degrees Celsius, which
it's a melting melting of an iron. More than that. Yeah, 1800 would be the iron melting temperature.
So obviously you have to have water cooling to keep it cool.
Right.
Inside.
Probably about 30 liters per minute.
What's that?
30 liters per minute?
No, actually we keep the chamber at about boiling temperature.
Boiling temperature. But how much is the flow?
Really typically it was about 5 or 6 liters per
Only?
minute.
Oh, okay, it's not so bad. Now we have this gauge in here.
That's a controller for controlling pressure.
Okay, controller for the control. And then you have a fan. What is that fan for?
That fan is for making sure that the bottom there stays cool enough because it doesn't have any liquid cooling.
Now we have this stuff. A few words about
this is a residual gas analyzer. RGA.
RGA.
And another capacitive manometer.
Right.
And then a molecular sieve trap.
Right.
To help purify the gas.
And how the process looks like for growing the crystals from the beginning to the end of it.
Right. The process for growing a crystal is actually very simple. What you do is you take, for example, in our case, silicon carbide powder. You heat it up till it vaporizes, and then you condense it on a seed crystal.
Right.
And if the conditions are exactly right, silicon carbon arrives simultaneously at the seed crystal and makes silicon carbide.
Right.
If the conditions are not perfectly right, they don't.
Yeah, but you could have a similar structure only with a greater pressure to create diamonds as well.
No, diamonds actually.
Oh, you're gonna have to have a graphite, right? As at the beginning of it. The carbon. I'm sorry. The carbon.
Yeah, but the furnace itself is carbon.
Yeah.
And so, when you make diamond is actually more difficult.
More difficult to process.
Yeah.
But I saw a small machine, very small machine.
Doesn't take a big machine.
Yeah, doesn't take it. So actually, are you saying that making a diamond is easier than making the crystals that you
Making a diamond is easier than making, for example, a 6-inch diameter silicon carbide.
Right.
Or making a few carats of diamond is much easier than making, say, a kilogram of silicon carbide. Right. So the silicon carbide crystals are actually big crystals.
Yeah. Well, this video is dedicated to youngsters, young scientists, the people who are interested with science, to show what the man can do. And this is everything that you see in here is a custom made. It's a beauty of its own. I don't have a place for it. Okay, we have another thing in here.
That's just a steam generator that we use to purify the inside.
Right. And that's how the dower for the liquid nitrogen looks like.
This part I use for making high purity nitrogen.
Okay, how do you do that?
Okay, the way we do it here is we have a chiller.
Right.
This basically cools the air down.
Minus 20?
Well, actually just above freezing.
Oh, just about freezing.
So that the water vapor drops out of the air.
Right. And then it goes with the pipe. With the pipe goes in here, and we have a nice
through to coalescing filters.
Right.
Then it goes to a membrane.
Okay.
That separates nitrogen and oxygen.
Right.
So nitrogen comes out here Oxygen goes up.
And then you have a filter.
This is actually a
Okay, catalyzer.
Final drying stage.
Catalyzer.
Yeah, catalytic dry.
Yeah, and it is made from
Copper sulfate.
copper sulfate.
Very, very simple, straightforward.
Right. And then what is in this big
Compressor.
compress? Oh, because you don't want to have that. No, okay. Now we have another stuff.
Oh, that's not actually currently being used. This is just a chamber that we can put more dryer in it.
Okay. And then we have something else in here, and that is...
That's actually a really high temperature pyrolytic purifier.
Okay.
Which removes impurities.
And then we have a huge tank. And we have a catalyzer again.
This is the output to catalyze the output.
Right.
This is just a big tank for storing.
Okay. And that filter is for...
Keep the air clean.
Okay. And this is the storage one.
Right.
Okay.
This is actually what we use for chilling, cooling the reactor.
Okay, cooling reactor.
So all we do is we run water through the reactor and through a air to water.
Yeah, but you have a Electron.
Yeah, this is a low temperature chiller.
Yeah, low temperature chiller. This one goes to -20? It will. It will.
This one will not quite to -20.
Yeah. And then we have all of this part of the pipes.
Manifold just to distribute water to various parts of the reactor.
Okay. So that's how the scientific entity looks like from inside. I was lucky enough to be allowed to put it for others to enhance them. Okay, we have something that would be good for the samples preparing for the electron microscopes.
This is a lapping system.
Yeah.
Lapping.
But how nice sample I could have.
It'll polarize.
Yeah. I gotta buy something like that. And this
thing new. Believe it or not, it's about $50,000.
I might be able to get it for a few hundred for you. Can we go here?
Yeah, this is a wire bonder.
Yeah, well,
it's for attaching the wires to a semiconductor, the very fine gold wires.
Right, and then we have this part. Transparent, right, for us, and it goes to 1,000 degrees Celsius.
When it's at 1,000, it's actually, you can see through.
Oh yeah, it's red.
Yeah, because the gold reflects the infrared, but it's transparent, visible. So.
Right, and then we don't have the beauty check over there. The beauty check. Okay, that one. Yeah. Okay, a few words about that.
This is just a probe station. I'm probing an ultraviolet light emitting diode that we use for air purification and water purification.
So you have two contacts in here, and then you have a specimen under the test.
Right.
And then
voltage.
Yeah, you have a beautiful power supply, and it gives you exact changes of it. And then optometer. If you follow that wire, right, you go to that beauty in here. Is it photomultiplier that is there? No, it's a photodiode.
Silicon
photodiode.
Ultraviolet.
Yeah. Okay. So that's a beauty. And what about that crystal? Could you say?
It's a sapphire crystal.
Sapphire.
It's actually grown this way.
Okay.
It doesn't work with sapphire. Sapphire isn't.
No, I know, but I'm trying to.
Silicon for
Yeah, silicon, right. Doped, right.
To make it simple.
Right. Now, how you cut it?
This is cut with a multi-wire saw.
Right.
So.
Oh, you have a multi-wire saw?
Wire with. We had one here.
Yeah,
but it's now in our Russian.
Okay, I gotta remember if you need one. Okay. Okay, that's the end of the video. Thank you very much.
Yeah, well, I don't need another.
Oh, you need it? Yeah. But that's a beauty. And then, I never asked you. When you have that crystal, let's go over there.